everybody, it's Miss Mizzy. Today we're going to be talking about rational numbers, but before we talk about rational numbers, we have to kind of gear ourselves up to understanding what rational numbers actually mean. Now, for those of you who have had me before, you understand the number rainbow that we talk about. It's called the real number rainbow. And when we deal with the real number rainbow, we're talking about real numbers and not imaginary numbers. Imaginary numbers come in 8th, 9th, and 10th grade when you're dealing with Algebra 1 concepts. Mostly in Algebra 2 is when you deal with it in high school. So let's focus in our real world. These are numbers that we deal with on day-to-day basis and real world situations. So our rainbow does not have as many layers as a real rainbow. So I'm going to start out with blue here for color coding purposes when we're dealing with rainbows. And this is the bottom level. The bottom level is what is called natural numbers. Now, natural numbers are your counting numbers. We're talking about when you turned 1, 2, 3 years old and you knew how to count from 1 to 10. You started out with 1, 2, 3, 4, and you learned on from there. Now, the next grouping of numbers are called whole numbers, and there is very little difference between natural numbers and whole numbers. This is when you started to be in kindergarten, first and second grade, and kind of understood what the number 0 represented. There was actually a number that represented nothing. So whole numbers are 0, 1, 2, 3, and it continues up to infinity. The next grouping of numbers are introduced actually in 6th grade. We start learning about negative numbers as well as how they correlate with positive numbers and also negative numbers and their distance away from 0. Now, prior to 6th grade, you may have seen integers in science when dealing with temperature. So these are numbers, and we'll just talk about this, all the way from negative infinity will include numbers such as -3, -2, -1. It includes 0, 1, 2, and 3. And it continues. So it continues both ways from positive infinity and negative infinity. And now we come to our rational numbers, and that's what we're going to be talking about today. Very important about these rational numbers. They include terminating decimals and repeating decimals. So those two terms are going to be what we're going to be talking about today as well, and the difference between the two. Now, I have written down some examples of rational numbers. I made sure to include whole numbers here. Of course, it includes our actual integers, as well as 4 2/10. This is a terminating decimal. It's a decimal that stops. 1/2 we know is 5/10 in decimal form, so of course that's a terminating decimal. And here we've got 8.2 repeating. If everybody can take note of that bar above the 2 there, that is a repeating decimal. So I'm not going to go too much into detail about irrational numbers, but as you can see, I have drawn a cloud and put the term irrational numbers there. We're not going to be talking about that term during this video. However, there will be another video coming up soon just about irrational numbers. But I want you to understand that in the world of real numbers, irrational numbers coexist with rational numbers, integers, whole numbers, and natural numbers. So what does this model in front of us even mean? We have a bunch of colors here. We have a cloud. We supposedly have a rainbow here. What does it mean? Well, this model is used for classifying numbers. And we can classify numbers in different sets. So if I were to talk about the number 1, and the number 1 is shown here, of course, and the number 1 fits in the set of natural numbers, whole numbers, integers, and rational numbers. However, if we're talking about something like 1/2 only fits into the set of rational numbers because integers do not include fractions, whole numbers definitely do not include fractions, and natural numbers do not include fractions. So let's take the term rational number and kind of define it. Now, a rational number is any number that can be written as a over b, where a is an integer and b is a non-zero integer. That means that the denominator in any number cannot be 0. Now try and recall when I was talking about the real number rainbow that a rational number also includes terminating decimals and repeating decimals. Now, a terminating decimal is exactly what it sounds like. It's a decimal that actually has an ending or stops. We can figure out if a fraction has a terminating decimal by dividing the numerator by the denominator. Same thing here with the repeating decimal. Same digit or group of digits repeat forever. So let's talk about a real-world example to kind of figure out, well, what exactly is a terminating decimal? So we can be given fractions upon fractions and just assume that they're rational numbers, but sometimes the actual value of the fraction might actually be an irrational number. And again, we'll talk about that in another video called irrational numbers. But for this one here, let's take a real-world example of batting averages. So in the sport of baseball, batting averages are determined by the number of hits divided by the times that the actual player is at bat. So let's say we have this example. A certain baseball player had 125 times up at bat and actually hit 36 of those 125 times. We would write the fraction as 36 over 125. Now we look at that and think, well, a lot of fractions are rational numbers, but we actually have to make sure that this decimal turns out to be terminating or repeating for it to be a rational number. We read this problem 36 divided by 125. Let's put it in a long division problem. The dividend is the numerator, the divisor is the denominator. We know that 125 fits into 36 0 times. Let's add our decimal here and make 36 look like 360 so we can actually obtain a number past the decimal. 125 fits into 360 2 times. 2 times 125 equals 250. We subtract and obtain 110. We need to add another 0 and bring it down. 125 fits into 1,100 8 times. 8 times 125 is 1,000. Subtract, get a difference of 100, bring down your 0. 125 fits into 1,000 exactly 8 times. 8 times 125 is 1,000. Take the difference, we're done here at 0. So of course, this answer is 0.288. We've got a terminating decimal. We stopped. This does not continue on. I'll let you know of a huge misconception that I see way too often. A lot of times, students will stop at the hundredths place and think, well, it's probably just going to go on repeating, or it's going to go on in a random of sorts. I'm a little bit too lazy to see if this actually does terminate, so I'm just going to assume that it's an irrational number. That's not the case. If we're actually trying to figure out if numbers are rational or irrational, you need to continue with your division until you find out for sure. So now we're going to be talking about a repeating decimal. Now this takes a bit of work and a little bit of a really good eye to be able to see if the decimal that you're trying to find is repeating or not. 27/99 is a great example of a repeating decimal, and I will show you why. Let's put this in a long division problem to make sure that we have a repeating decimal here. We knew that 99 could not fit into 27, so that's why our quotient bar has a 0 here. We added a decimal and made 27 look like 270. 99 fits into 272 times. Multiply 2 times 99, you obtain 198. Subtract, you get a difference of 72. 99 fits into 727 times. 7 times 99 is 693. We take the difference, we find that it's 27. 99 fits into 272 times. 2 times 99 is 198. We now have a difference of 72. This is where a really close eye is beneficial in this case. We've got a pattern going on here. Look at your differences. We started out with 27. We had a difference of 72. Then we had a difference of 27. Now we have a difference of 72. It is a coincidence at this point that the two digits are flip-flopped in both of the numbers, 27 and 72. It's not always going to be like that. We're literally looking for the pattern of this number shows up, then this number, then the previous number, and on again. This means that this is a repeating decimal. We can now put our final answer as 0.27 with a bar over it. The bar means that whatever numbers or digits are underneath the bar repeats in that same pattern forever. So the next time you're looking up in the sky, I hope you see a rainbow and it reminds you of the real number rainbow. Hope you enjoyed this lesson.